Okay, let's get started. Cool. So as a recap of last week, we talked about multitask reinforcement learning and how we might want to have reinforcement learning agents not learn just one task, but multiple different things that might correspond to multiple different reward functions. And we saw that we can formulate an aggregated MDP that encapsulates all of the different tasks where you now are augmenting your state with some sort of task descriptor, like a prompt or a goal or just an index corresponding to what the agent should do. And the way that this worked is we'd sample some task, kind of run the policy in the MDP for that task, sample another task, and so forth. And we would then get a policy that could be able to successfully achieve high reward in a number of different MDPs, or in another way to view it, a single aggregated MDP with this augmented state. This is going to be a little bit different from meta-RL, so we'll see that some differences here later in this lecture. And we also somewhat briefly talked about goal-conditioned reinforcement learning, and it could just be simply viewed as a special case of multitask reinforcement learning where each task is trying to reach a goal state, and the task descriptor corresponds to that goal state. And so if your states are images, for example, then now you'll be passing as input to the policy both the current image and the goal image, and you'll be trying to reach that goal image. Or if your state, for example, is a vector, you'll be passing in two vectors, and the task is trying to reach some goal state. And you can construct different reward functions if you have discrete states or continuous states as some sort of, did you kind of reach that goal or reach close to that goal? And one of the things that's kind of nice about this goal-conditioned formulation of reinforcement learning is that you can actually do it in a self-supervised way. You don't need task descriptors. You don't need a different set of tasks that you've manually defined. You can just use a bunch of different states as kind of the tasks themselves. And a lot of different tasks can be formulated as goal-reaching tasks. One thing to note here is it can be pretty hard to train, but you'll be experimenting with a simple goal-conditioned reinforcement learning setting in your homework. Okay, so for today, we're going to be talking about meta-reinforcement learning, and specifically we'll be talking about what that problem statement looks like, and a class of meta-RL methods that I like to refer to as black box meta-RL methods. We'll start to get into what these methods look like and also some of the challenges that they face. So what's the problem? Like, why do we care about meta-RL? Why not just do vanilla RL? So say that you're trying to figure out how to operate an espresso machine that you've never used before. If you wanted to do that, well, first, if you wanted a robot or a reinforcement learning agent to do that, it would probably take a lot of data, a lot of attempts to try to figure out how to make coffee. Because it's a pretty complicated task, lots of different steps involved. You have to do those steps in sequence. And also, the reward signal that you get for this sort of task probably isn't going to be super detailed. But as a human, if you were to attempt this task, probably, if you had a little bit of instruction or some previous experience making espresso, then you could probably learn it in minutes, or maybe even less than a minute. So if you think about reinforcement learning, this gap between how quickly a human could learn something and how slowly it would take a reinforcement learning system to learn it, this is rather unsatisfying. And if we think about what is the difference between a person and a reinforcement learning system, one of the big differences is that people aren't starting from scratch. People already know how to move objects around with their hands. They might already know how to make coffee in other ways or with other machines, and they can leverage that experience and also some notion of semantic knowledge of what to do if someone tells you to pick up a cup and put it somewhere, or to turn a knob. And it can leverage that previous experience in order to solve this problem really, really quickly in compared to training a reinforcement learning system from scratch. And so experience with similar tasks, other espresso making machines, either espresso making on other machines or just general like motor control, following instructions, that sort of thing can be very useful when trying to solve a new task. And I mentioned this as a kind of example with espresso making, but this sort of framework of not starting from scratch is really general. So it applies to robotics problems where where you're facing a new environment or facing a new task, but it's also really faced by many reinforcement learning systems. As another example, say you want to solve a challenging math problem that you haven't solved before. If you have experience solving previous math problems, then you can use that to more quickly solve a new problem because you've learned some sort of strategies that you might be able to apply to the new scenario. Okay, we're framing this question of can reinforcement learning algorithms leverage experience from previous tasks in order to learn a new task with less data and less experience. In many ways, this problem is thought of as a transfer learning problem where we want to transfer knowledge, information, experience from previous tasks to new tasks. And there's a few different formulations and a few different kind of problem settings that the research community has thought about. One is kind of a fairly simple setup where you learn one task and then want to learn a new task. And you can just, for example, train on one task and then fine tune on the new task. And notions of fine tuning that we use in supervised learning are also applicable to reinforcement learning settings, where you could fine tune a queue function to a new task or fine tune a policy to a new task. Although for this to work well, the tasks need to be quite similar to each other. We also talked about multitask learning, and you could also use multitask learning for transfer to new tasks. And in particular, if your prompt shares some structure, if it kind of exhibits, if it's just like a task 1, task 2, task 3, transfer is going to be harder. But if it's something that has a lot of structure, like pick up a water bottle, pick up a phone, pick up a pen, and so forth, then you might actually be able to have things transfer what's called zero shot without any new experience at all, simply by passing that prompt to the system and having it kind of act according to that prompt. And then meta learning is often concerned with, instead of zero shot transfer, something that's called few shot transfer, where you, with a little bit of experience, a few examples, or a few trials at a task, can you adapt to that task? And essentially the difference between multitask learning and meta learning is that it accounts for the fact that we're going to be trying to adapt with a small amount of data. And it does that during the kind of original training process. And another way of thinking about this is that instead of having the task descriptor be like a prompt or an index, the task descriptor might actually be a data set itself, like a set of trials that you're going to be adapting to in the context of some policy. Another word for this is sometimes in-context learning or few-shot learning. Now, for this to work, for the first scenario to work, you must have very similar source and target tasks. Whereas in some ways that things get a little bit easier and a little bit harder for number 2 and number 3. They get easier in the sense that you no longer have to have an extremely similar task. You instead just need to have a distribution of tasks and be similar to that distribution, such that conceivably the new task that you're trying to solve should be within the distribution of things that the tasks that you've seen during training. It gets a little bit harder because you do actually need like a number of training tasks, not just a single training task, in order to get effective transfer. Okay. Before we jump into meta RL, let's just look at a couple few-shot learning examples outside of RL, and then go back to the RL setting. So actually, I picked this example so that it's not like trivial. There's other test data points that are much, much easier. Cool. So that's kind of the essence of a few-shot image classification problem, where you have a small number of data points, and your goal is to classify a new data point. And typically, if you were to train from scratch on just 6 images, you'd have no hope of being able to learn a classifier, especially on high-dimensional images. But the way that meta learning works is you can construct other tasks for the machine learning system to solve that have a similar structure, like other image classification tasks. Train it to be able to take as input a training data set and a query image or a test input, and then predict a label, and basically constructing each of these few-shot learning problems as a data point themselves. Now, another example of few-shot learning outside of reinforcement learning is in-context learning in large language models. And what this looks like is, here's just one example. There's lots of examples of different tasks you could do. In this case, the goal is given a sentence that's kind of poor English input, like I eated the purple berries, output good English input, like I ate the purple berries. It gives it, in this case, I think, 3 different examples of input outputs. This is the training data set, and the goal is for a new input, be able to predict a good output for that example. So here's another example kind of a few-shot learning problem. And again, language models get things that kind of look like this during training. One thing that's a little bit special about language models is that this sort of in-context learning, you don't explicitly set up your training data set exactly to match all of this. And it turns out that a lot of the statistics of data on the internet leads to this ability to react to these few-shot examples effectively. This is actually just a base model. I think this is from GPT-3. And so even without any additional supervised training, you get something like this. It's not perfect, doesn't work all the time, but this is another example of few-shot learning. And then in each of these examples, you can think of the goal is trying to train this sort of model that takes as input a training data set and a new example X and makes a prediction for that example based on both X and on the training data. Yeah, so the question is, in context learning and LLMs, typically you achieve this sort of model and this sort of few-shot learning through prompting by putting the data set in kind of as context or as part of the prompt into the model. Is that also how it works in MetaRL? Generally, yes, we're going to be looking at that case in MetaRL. There are actually other methods where you can accomplish this with gradient updates as well, or with something that looks like nearest neighbors. The most successful method in MetaRL looks like prompting, and so that's what we'll be talking about today. Now, let's look at a MetaRL example. So, say that we want to navigate mazes. And so our goal is we want to solve a new maze. And we're an agent that's in this maze. We don't get to we actually don't even see this top-down view. Maybe we just have a first-person perspective. And our goal is, because this is a reinforcement learning problem, it's not just about outputting a label. It's actually also about collecting experience in the environment. And so kind of the goal is we'd like to be able to very quickly solve a reinforcement learning problem. And we'll frame this as collecting a very small training data set of one episode or a few episodes. In this case, it's kind of exploring the maze, trying to find where the goal is. And it kind of starts in the middle right here, explores over here, and it eventually goes to the goal right here. And after we explore, we'd like to be able to have a policy that is able to solve the maze. In this case, just with a single episode of experience. And again, if you were to do this sort of thing from scratch that tries to use just a single episode of experience to get a policy that can solve the task, this would be very, very hard. And instead, the way that MetaRL frames this is by trying to construct examples and try to construct kind of a set of training environments that facilitates this kind of fast adaptation. Now, in comparison to the supervised learning scenarios, like I mentioned, we're now going to be faced with this exploration problem. We're not just given a training data set and then make a prediction based on that training data set. We're actually constructing the training data set ourselves through exploration. And we need to figure out how best to trade off between exploring in the environment versus being able to then solve the task, and how much time we should spend exploring versus trying to exploit what we know about the environment. So if this is our goal, this is what we'd like to be able to do at test time. We'd like to be able to quickly learn a new maze. Then to set our agent up for success, at meta training time, before we try to adapt to a new maze, we'll try to learn how to efficiently explore and solve many other MDPs that are related. In this case, they can be other mazes like this and so forth. And these are each of the tasks that we'll be training on in order to adapt to a new maze. Cool. The other thing, I guess one key assumption here is that you need to have, these new MDPs can't be completely different from the MDPs that you saw before. And the way that we can think about that is we should have some sort of distribution over tasks. And these new MDPs that we're trying to adapt to should be within the distribution of tasks that we saw during training. Okay. Maze navigation is like one example of a meta-RL task. There's lots of other scenarios as well. So one useful scenario that we've seen in robotics is being able to adapt very quickly to different terrains, different slopes for legged robot systems. This is actually a really small legged robot, but it's also applicable to larger legged robots as well. And sometimes you might actually be training on different environments in simulation and then adapting in the real world as just another environment. You could also have object manipulation as different tasks as well in manipulation scenarios. And then there's also a number of language modeling scenarios where this is quite applicable. One example where meta-RL has been relevant is adapting to different users with different preferences, where you give examples of the kinds of things, the kinds of responses that they want in context. And we'll also later see an example in reasoning as well. Yeah, so the question is, like, what is the key difference between this sort of meta-RL approach and transfer learning where you're training and then fine-tuning? And there's a couple of ways to view it. One is that during this kind of training process, you're actually explicitly optimizing for transferability. You're optimizing for the ability to adapt with a small data set. And as a result of that, you can get much faster transfer. You can use a much smaller data set. And there are examples of, like, if you use fine-tuning versus if you use like few-shot in context learning or few-shot adaptation, you can get much more efficient transfer. And yeah, so you get much greater efficiency. And the way that you get that is by providing the algorithm with a number of different training tasks rather than like just one training task that you're feeding off of. Okay, so slightly more formally, we've talked about multitask learning, where you try to solve multiple tasks at once. You might try to transfer to a new task from that, but you're not optimizing for transferability. With transfer learning, you're trying to solve some target task after solving some source task, typically by fine-tuning. Whereas in the meta-learning problem, we have experience from some training tasks, and we want to very quickly solve a new task. And in the reinforcement learning scenario, these tasks are going to be MDPs, each with their own state space, action space, dynamics, reward. And there is this kind of nice, we see kind of meta learning and supervised learning, and there's also, there's kind of a nice analogy between the two, where the main difference with meta-RL is this exploration challenge. Okay, and then diving into some notation here, we can view the meta-RL problem as basically being able to, with a small amount of experience, be able to learn a policy that can solve the task, and also to be able to collect this experience itself. And so this training data, there's two different variants of the meta-RL problem. In the first case, this can correspond to multiple rollouts from some exploration policy. And instead, you could also consider this to be just actually a few time steps from your exploration policy. There's a bit of a continuum between these two scenarios. You might want to be able to adapt both online with a few time steps and with more and more episodes with basically kind of a growing data set. But writing it kind of explicitly as two different things here to kind of make it clear that there are some problem settings where you want to adapt really quickly online within an episode, and other scenarios where you're caring a lot more about kind of multiple trials of experience. The last thing that I'll mention is I've been writing it as a kind of an exploration policy and a task policy. There are some scenarios where you might train these, and these might be separate networks. There's other scenarios where these could share parameters and basically be the same network. So they don't necessarily need to be separated like they are on this slide. And then the last thing is, insofar as we're learning this policy that's conditioning on a training data set, you can sort of view this as a task identifier. And from that standpoint, we're then kind of more in a setting that looks like multitask learning. So the question is, when I say that the test task should be in distribution compared to the training task, does that mean it has to be the same as one of the training tasks, or can it be a bit different? It can be a bit different. So and we'll see examples where it is different as well. So let's talk about how to address these problems. So the good news is that there's a kind of a very conceptually simple way to address this kind of general problem statement. The bad news is that it can be challenging to optimize in practice, and we'll talk about some of those challenges in a bit. But conceptually, we can essentially train a sequence model. It could be a transformer, any sort of neural network with memory, a recurrent neural network, and use this where basically everything that's being passed into this policy corresponds to the experience that the agent has collected. So you're basically conditioning your policy on this training data set, and then having a policy output actions based off of the data that it's seen so far in that MDP, and then training this the sequence model policy across all of the set of training MDPs that we have. So here, this is the current state. This sort of context or training data set is going to get larger over time as we collect more experience in a given MDP. Now, a question for you. There are a couple differences between this and simply using a recurrent policy in a standard RL setup, or using a sequence model in a standard RL setup, like using a transformer. Does anyone have thoughts on like what are some of the differences between kind of what I'm starting to talk about here and simply using a sequence model as your policy in kind of a standard RL setup? Memory. Yeah, so typically in RL, we often don't use memory, and here we're using memory. So that's one thing. But like compared to if we had used memory in like a standard RL setup, what else is different here? Yeah, so one thing that we're doing here is we're actually passing the reward as input into the memory, and that's a little bit different in the sense that you're actually using reward information from the current MDP in order to try to get better at the task. This also means that actually at test time, or when we're trying to adapt to a new task, we're also going to be using the reward. And in RL settings, oftentimes we don't necessarily assume that we have the reward when we're just deploying our policy. Okay, so that was kind of one main difference. Any other differences? Yeah, so the question is, why are we also not passing as input the actions? You can pass as input the actions. It depends on, like if your policy is mostly deterministic, then information about past actions could be stored in the memory as well, because you generated those actions. And so in those cases, you don't need the actions. If you have a more stochastic policy, then that sampling process won't be necessarily in the memory. And in those cases, it's good to pass as input the actions as well. Right, so the note was that the states and actions might not be the same for different tasks. And so one of the things that's different here is we're actually training this model across MDPs. And so you might have a different state and action space, you might have different dynamics. And so because like one of the big differences compared to standard RL is that we're training this across MDPs, and there's gonna be differences in states, actions, dynamics, and rewards across those MDPs. Cool, there's actually also one other difference, but the first thing that we talked about is see that the reward is passed as input, you might also be passing as input actions, and this is trained across multiple MDPs. And that's quite different from the typical reinforcement learning setup. Now, the second thing that's also different is that your memory is also going to span across multiple episodes, potentially. If you're trying to actually learn not just within an episode, but learn across episodes, then rather than having your current policy simply have memory within an episode, you will be maintaining any sort of hidden state or any sort of memory, not just within your episode, but across multiple episodes. So in terms of what this algorithm, maybe I'll leave this up here in case it's useful. In terms of the algorithm, what this looks like is we will sample a task or an MDP. So maybe let's call this MDP TI. And then we're going to run our policy in that MDP for multiple episodes. So let's say run pi in our task or our MDP for n episodes. So this is rolling out this right here, and it's going to have memory across those n episodes. And then optionally, if we're using an off policy algorithm with a replay buffer, then we would store the episodes in a replay buffer. And then lastly, we're going to update our policy to optimize the rewards. And so we will be updating pi, and specifically, we are going to be maximizing the sum of rewards, like the typical RL objective, but it's going to be across all of the tasks in our task distribution. So we'll have some sum over tasks I in some mini batch, and then also the expected sum of rewards. So this would be an expectation under our policy of the sum of rewards over different time steps. Now, this is a pretty simple algorithm. It looks a lot like reinforcement learning, where simply the main thing that's different is now we're going to be doing this optimization across multiple MDPs, and our policy will have memory across a set of episodes. Usually this is going to be pretty small, because if it was large, if it was like 1,000 episodes, it's going to be hard to store that in the context of a model, like just because your memory will start to increase substantially. So what that looks like is you have this like neural network. It has multiple episodes, and then you'll be kind of rolling it out for multiple episodes, taking actions, and then you'll start collecting for a new MDP. So you'll cut your memory when you start to collect for the new MDP that you've sampled. So you sample a task, roll out the policy for n episodes. In this case, n equals 2 in this diagram, under the dynamics and reward function for that MDP. Then store in your replay buffer. Oftentimes you'll have a different replay buffer for each task. And then update your policy to maximize the discounted return for all tasks that you've collected for. And then repeat this process in order to continuously get a policy that's better at doing this sort of in-context adaptation. Yeah, so this is a good question. So the question is, does it know that it's starting a new episode, like at this position right here? You could use a position encoding. In practice, you're also going to have probably have a discontinuity in your state. And so you might just be able to see that like your current state is very different from the past state, and that might also tell it. But yeah, you could have some sort of token to also tell it that it's a new episode. The question is, are we randomizing S1 across the different episodes? When you're rolling out the policy, when you start a new episode, you'll sample, that will be a different sample from the initial state distribution. And so S1, I guess it's maybe a little confusing. S1 here, it might be different from S1 here. S2 is very likely different from S2 here, and so forth. Cool. And then the outcome of this is you'll have a policy that should be able to adapt across episodes with experience from those episodes. And it should be able to, on its own, actually decide on the best exploration-exploitation trade-off. And the best exploration-exploitation trade-off is going to depend on the number of episodes that you give it. If n is 2, then it has 2 episodes to maximize rewards as quickly as possible. And if it needs to explore, it'll explore as quickly as possible. If n is a little bit larger, then you've given it a little bit more budget to, it still wants to explore quickly and efficiently if it can, because then it can get higher rewards later, but it might have slightly more budget to explore. And so you'll get, one of the things that's like pretty cool about this, when you optimize this whole thing end to end, is that it will make decisions on whether or not to explore or to exploit. And it'll make those decisions in a way that's informed by whatever gets it the highest reward. Then after this sort of training process, after you've trained it on multiple MDPs, then you can actually then roll out your policy in a new task. So at test time, you will then give it a new task. So you're in some new MDP TJ, and you can take the policy that was trained and roll it out in that MDP. So roll out pi in that MDP with those states, actions, and rewards, and so forth. And so sample a new task, roll out that policy. You want to roll this out for up to n episodes. If you roll it out for longer, all bets are off in terms of what it might do. You could also, you could also have a variable number of episodes that you use during training if you want it to be able to handle variable numbers of episodes. But yeah, this would be like for n episodes or for up to n episodes. Cool. So in terms of actually implementing this, there's a few different architectures and optimizers you could use. So you could use like a vanilla recurrent neural network. Some of the first works on meta reinforcement learning did this. And they used algorithms. This is, I think, before PPO existed or was introduced. They used an algorithm that's somewhat similar in nature in terms of the assumptions as PPO. There's also a model that, a paper that before transformers were really popular, used self-attention and also 1D convolutions. You can think of it sort of as a transformer and optimized this. And you can actually note that they do also pass the actions as input in this particular scenario. One other thing, we'll talk about this a little bit in a bit more later, but you can also, instead of using a transformer or an RNN, you could also use a feed-forward network and then average across, average the embedding. This is sometimes called a deep set. And it has its own benefits. It's actually pretty computationally fast because you can parallelize everything, and also actually surprisingly expressive for what it can do. So let's look at some examples. So we'll look at this example that was using something that's kind of a bit like a transformer. And they were trying to learn how to visually navigate a maze, specifically new mazes that the agent had never been in before. They trained it on 1,000 small mazes, and they tested it on held out mazes that the agent hadn't seen before. They tested it actually on small mazes and on large mazes. This is actually a scenario where they were able to see some extrapolation to tasks that were outside of the distribution of what it was trained on. So this is what it looks like. So this is at test time, and you can see that the agent, it just is like exploring around this environment, looking for where the goal is. It only gets these images as input. And on the right, we can see the trace of the exploration. So it started in the middle, explored over here, and explored down here, and eventually found the goal. And then after that exploration episode, we still have memory from that previous episode, and it's able to, using that memory, it's able to then be able to kind of go directly to the goal based on its experience in that maze. So kind of watching that again, whoops. This is the first episode, and so this is kind of the first episode of rolling out this policy. It's choosing to explore because it doesn't know where the goal is in this maze. It also doesn't know the layout of the maze. And so we see it explore here. And then in the second episode, it chooses to go straight to the goal because it decided that it already explored the extent of the maze. Here's an example in a larger maze. So the agent starts over here. And it explores in the top part, doesn't see the goal and realize that this is a dead end. It doesn't need to explore it further. And then it ends up seeing the goal here. And then after that, it goes straight to the goal after that first episode. And so in this training example, n equals 2. So they trained it just to be able to explore and exploit after 2 episodes. Cool. And then quantitatively, they looked at the average time to find the goal in both the first episode and the second episode. They compared to using a random policy, which occasionally does happen upon the goal, and using an LSTM architecture and this more kind of self-attention and convolution architecture. And they found that with the small mazes, even within the first episode, they were able to do a lot better than random. That's because it's actually exploring efficiently and then eventually often finding the goal. And then it's able to find the goal faster in the second episode after learning where the goal is and about the maze in the first episode. And we also see that it does significantly better than a random agent in the large mazes. And in both cases, using kind of the self-attention architecture is better than using an LSTM architecture, which is another memory architecture. Yeah, so the question is the reward to find the goal? And if so, why is it optimized to find it as fast as possible? So the reward is to find the goal. I don't remember the exact structure of the reward. It's optimized to find it quickly. There's a couple ways that lead to it to optimize to find it quickly. In this particular case, I believe they're using discounted rewards. And so the discount factor, instead of being like this, you're optimizing for discounted rewards. So there's a discount factor right there. And the discount factor is not 1. It's probably 0.95 or 0.99. And so that objective will be higher if you get the reward sooner rather than later. Yeah, so the question is, what is passed input to the model? And yeah, exactly. So it's video from the previous episode, the actions from the previous episode, and basically everything up until the current time step, which is any previous episodes and everything so far in that episode. So it's all of the video frames, and then also all of the actions and all of the rewards as well. Yeah, so the question is, where in the algorithm are we exploring exploration versus exploitation? And here, because it basically all comes down to this objective for both of them, and the insight is that the agent doesn't know much about the task. It doesn't know, well, depending on the training tasks. In this case, it doesn't know what maze it's in. It doesn't know the structure of the maze and that sort of thing. And so it's actually it's not able to get high reward until it starts to explore, until it finds where the goal is, for example. And so by optimizing just end to end for reward, you're incentivizing it to, it's not going to get high reward without exploration, essentially. Yeah, we will talk about that soon in a few lectures. But yeah, there's lots of problems here because when your policy is bad and you're not getting good rewards, it ends up being very difficult to figure out a good policy. Yeah, so the question is, instead of doing what we're doing, could we just do regular RL and then do test time training? So in some ways, language models with recurrence, it depends on how you view it, but in some ways you are already doing something that kind of looks like meta RL if it has memory. And it basically has the ability to adapt depending on the kind of the task that you're giving it. And then one important component is if you're doing test time compute, you're allowing it to actually think through the problem. Now test time compute is a very broad term. So on the next slide, we'll talk about how you can actually use, how meta RL is relevant for test time compute. So let's talk about that now. So say that we're solving different math problems. This is the canonical language model example, especially for test time compute. And one example of a math problem is trying to show this inequality. This is actually the same, I think possibly the same math problem that Avral showed in his lecture. And in some ways, trying to solve this math problem is, you can think of it in some ways as an MDP itself, in that there's different strategies that you might try to take to solve this math problem. And you don't know a priori which strategy is going to help you solve that problem. Which kind of where do you start? Like, do you try to, for example, do guess and check? Do you try to eliminate terms in the equation and so forth? And ideally, you'd be able to kind of explore those different strategies and then produce an answer based off of the best strategy. And it turns out that if you give, so DeepSeek R1 is a language model that uses test time compute in order to solve math problems. And if you give R1 different math problems to solve, if you give it a hard problem, it kind of thinks for a while. At some point, it cuts off its the test time compute because it doesn't want to be thinking for too long for the user, and then it outputs some explanation for the user. And then also, if you give it a really easy problem, like 2 + 2 = question mark, it actually also kind of thinks through what the solution might be and then gives a step-by-step explanation for the answer. And so this is something that is clearly somewhat wasteful to do, probably, unless this is somehow a challenging problem. And so you can actually use this notion of meta-RL to try to optimize for test time compute. And if you know that you're going to be doing test time compute at test time, then basically bring that into the training process and encourage the model to efficiently use that test time compute, efficiently explore different strategies, such that ideally on easy problems, it is trying to output an answer as quickly as possible. And for harder problems, it's thinking as much as it needs, including possible exploration, until it then tries to exploit and give an explanation. And so this paper here was a paper that explored that. They found that when they were trying to explicitly optimize for effective use of test time compute, they were able to get higher performance with the same number of tokens, and also actually reduce the number of tokens needed to get the same performance, so that you aren't, for example, using up a ton of tokens on simple problems. So that's a use case of meta-RL or ideas for meta-RL in language models. Now, a quick digression, and this will actually lead us into a different way of thinking about meta-RL. So we've talked about multitask policies where we condition on a task descriptor. So maybe we want a robot to stack in different locations or a robot to walk in different directions. And we've talked about policies that take as input experience and then kind of generate actions based off of that data set. And if you were to think about how this relates to multitask learning policies, one way to think about it is that we're just doing multitask learning, but now this data is our task identifier. And it's something that actually changes within a task. So the analogy is not perfect, it's not actually fixed for a given task. But you can sort of think about it as conditioning on the task insofar as experience tells you what the task you're trying to do is. Cool. And if you think about goal condition policies, rewards are, you can sort of also view meta-RL as a kind of a generalization of goal condition policies, because there's a set of MDPs that are goal-reaching MDPs, and then there's a broader set of MDPs that are reward-maximizing MDPs. And then the other way to think about this is instead of trying to generalize to new goals, you can think about meta-RL as trying to adapt to new tasks with a small amount of experience. And this would be kind of the difference between zero-shot generalization in the goal condition case and k-shot generalization with k episodes or k time steps in the meta-RL case. Now, so we've talked about how we can view the experience as the task descriptor Z, or the prompt, essentially. But there's actually another way to look at it, which is that if we think about this policy with memory, and that has kind of the past memory and then our current policy, if we were to think about what information is being passed right here to the policy, this information is presumably information about the task. And specifically, when ZI isn't part of the state, there's ambiguity about what MDP you're trying to solve, and you're using that experience to try to identify the MDP that you're in. And you can sort of think about it as the policy needs to infer the task. It needs to infer specifically some sort of latent task descriptor from its experience. And so another way of looking at meta-RL is something where you are using your experience to infer what the task is, and then conditioning your policy that's acting at the current time step on your current estimate of what the task is. So you can think about it essentially as meta-RL is trying to explore to infer this unknown task and then perform the task. I see. So you're asking like, because we're going to be inferring the task identifier, why don't we just give it to the learning system? Yeah. So the main reason is that if we don't have a compact way of describing the task that the agent is doing, then it may actually be like challenging. Like we may not have if we don't have a good way to represent it, then we're not sure what to pass into the policy. And if we don't have a good way of representing it, we can always resort to just using an index saying this is task 1, this is task 2, this is task 3. But if you do that, and then at test time you say this is task 100, it's not going to be able to generalize in that scenario and do anything about that scenario, about that task. Whereas experience, like conditioning on experience, is something that could generalize, where it can actually be able to use kind of the more continuous space of states, rewards, and so forth in order to figure out a new task. So it comes down to representations, and you could sort of view this as like learning a Z representation, like learning like a continuous vector that's representing our tasks. Now, in Multitask RL, we talked about how there was this, we talked about how if you like formulate some state space, that it corresponds to the original state space and the Z vector, then you get this aggregate MDP. And so the result of this is still an MDP, just with a new state space and like new dynamics to account for this new state space. And so there's a question of like, for meta RL, is there an aggregate MDP? And this would be for meta RL. And in this case, we're not providing ZI in the state. And so there's actually, like, inherently, it's actually partially observed. You don't actually know what the task is. You're trying to explore and figure that out from experience. And so there isn't actually an aggregate MDP that you could think about. Instead, if you wanted to try to aggregate it into a single decision process, it would have to be a partially observed MDP or a POMDP. And it's actually a special kind of POMDP, where we talked about before, where you have like some sort of partially observed Markov decision process where you can't actually observe S, and you have actions, and instead of observing S, you observe some observations that are some function of S. That would be kind of the general POMDP case. One thing that's a little bit special about the meta-RL thing is the only thing that you can't observe is what the task is. And so it's basically a POMDP where this hidden state space can be defined as the observation and the task identifier. And if you can infer the task identifier from experience, then you can essentially view it as a way of trying to infer the underlying state space as a way to solve the POMDP. So this is basically kind of another way of looking at the meta-RL problem. It's basically like a partially observed Markov decision process. Now, there's a meta-RL method that we actually talked about. I showed an architecture diagram that was actually explicitly trying to output Z's, and it was actually outputting some distribution over Z's. Because at the very beginning, you actually don't know what Z is. You have some kind of prior belief over what Z is, and then as you get more experience, you're going to have a better and better estimate of what Z is. And so if you represent a distribution over this kind of latent task representation, then you can do kind of cool things with that. And we'll see that in a bit. So this particular algorithm is looking at continuous control problems, where different tasks corresponded to walking in different directions, running at different velocities, and also different physical dynamics. So being able to adapt when the friction is different, or the inertia of the robot system is different. The other thing was that what we saw before was using like a PPO style algorithm, which is somewhat off policy, but not very off policy. It's kind of more on policy than off policy in some ways because it's not using a replay buffer of past data. And with meta-training algorithms, you can adapt really, really quickly, but the training process might be really slow if your base algorithm is fairly on policy. And so as a kind of question, hopefully this should be a straightforward question. If your base algorithm for updating the policy at step 4, if that's an off policy algorithm, do you expect that to be more or less efficient than if you used an off policy, or than if you used an on policy base method? Yeah, more efficient. So if you're using a replay buffer and using that replay buffer to update your memory, your policy with memory, that should be a lot more data efficient during this meta training process. At kind of a test time when you're adapting, the efficiency is going to be similar. So this is just talking about the efficiency for actually training this sort of in-context learning system. And so if you look at, if you actually look at the curves like over this training process right here, the amount of data that you need in order to kind of meta learn these kinds of systems, you can see that in blue, if we're using kind of an off policy algorithm with a replay buffer, it's a lot more data efficient, learns a lot more quickly than RL squared and POMP, which are using, well, actually all three of these are using base RL algorithms that are more on policy, more like PPO, for example. Yeah, so the question is, can I elaborate on what specifically is in the replay buffer? So typically you'll have, so each replay buffer will have a sequence of episodes. Basically each thing in the replay buffer will be a sequence of episodes from a given MDP. And that includes like the states, the actions, the rewards, and when you optimize this, you'll need to, oftentimes you'll have a different replay buffer per task, so that you can sample a task here, and then optimize the reward for that task using the memory from that trajectory. Typically the buffer, instead of just storing states and actions, you're storing full trajectories together because you're going to be training a model with memory, and you need to be able to provide that trajectory as memory, as input to the policy. Cool. So summary so far, we've talked about using these models to be able to adapt to new MDPs. They're general, they're quite expressive, and there's also a variety of choices in the architecture. One thing is that they're hard to optimize because it needs to figure out how to adapt from data, and there's lots of different input features here that you could try to pay attention to, and the model has to figure out what about those input videos that you're passing as input for the maze navigation is useful when you're then trying to exploit and learn a policy. So it's because you're passing in so many things as input, it's such a big model, it can be hard to optimize for that reason. And it can also be hard to optimize from an exploration standpoint, which we'll talk about right after this. And then like the sample efficiency of the meta learning process is going to be inherited from whatever optimizer you use in this last step right here. And so if you use something like vanilla policy gradient, it'll be extremely data inefficient. If you use something like PPO, it'll be more stable, but still fairly inefficient. If you use something like SAC, it will be probably a lot more efficient, although you might need to tune the hyperparameters more. So now let's talk a bit about exploration. By exploration, I mean like exploration in context, exploration when you're trying to explore a new task. What we've talked about so far is trying to optimize end-to-end for exploration and exploitation with respect to the final sum of rewards. It's simple in principle, it can actually yield the optimal exploration-exploitation trade-off because you're optimizing directly for the sum of rewards. And that's really, really nice, but it can be a really challenging optimization. And let's talk about why that's the case. So let's look at a running example. So say that you have some robot that looks like this, and the robot needs to find something. And there are some hallways that the robot might need to go down in order to try to find the thing that it's trying to find. And different tasks correspond to different locations of the object that it's trying to find. So in one task or in one scenario, it might be all the way over here. In another scenario, it might be over here, and so forth. And to help the robot out a little bit, we're going to introduce one other thing, which is that there's going to be like some piece of paper over here, and that paper actually says where the object is in words. Like it says that the object, like I don't know, maybe it's trying to find like a replacement light bulb or something like that, and it says the light bulb is in like the 4th hallway at the end. Okay, so here's our robot. Here are the hallways. Different tasks correspond to navigating to the ends of the different halls, and we have some information about where to go. And if we look at that, information will be in the state about where the reward is for this task. Now, how do we actually learn how to explore? So say that we were trying to collect trajectories and trying to learn how to explore such that we can get good behavior. So say that let's start with a scenario where we sampled a task, and maybe the task was to go to the end of this hallway right here. And say that we collected we actually kind of just got lucky. We collected a trajectory that just went straight to that reward. Now, in some ways that seems good because we got reward for that. And so that gave us some reward. And that's like optimizing the objective that we care about ultimately. But the thing that's bad about this is that the robot got lucky, and it doesn't actually know how to repeat that in the future because it didn't actually explore any other alternatives. And so this is going to be the way that we can kind of view this is that it goes to the end of the correct hallway, it'll get positive reward, but the context leading up to getting that positive reward doesn't actually look different than any other task. It kind of went through here, and there's nothing that kind of differentiates what it did there, which was like 0 reward, 0 reward, then if the task, for example, had been to go here or to go here. And as a result, it didn't actually learn how to explore, and it didn't learn how to use exploration information in order to solve the task. And so this trajectory might actually be very helpful for learning how to explore and learning how to exploit. Now let's say that we had a different trajectory. So we're exploring, and let's say that the agent, instead of doing that, it maybe sampled the same task, and it went to the end of this trajectory and then continued, didn't see that, and then went to the end of this trajectory. So that would be good in the sense that it does actually have, like, it did kind of rule out, it has experience that ruled out one task, and now then it got reward for a different task. And so it's going to be teaching it something about an exploration strategy that works. The downside is that exploration strategy is quite suboptimal, because it would have been a lot more efficient to first look at the instructions and then go to the correct position. And so it's somewhat good, somewhat bad. It provides signal on a suboptimal exploration and exploitation strategy. And so it's perhaps better than the first trajectory that it did, but still not ideal. Now let's consider a third trajectory. Say that we are, again, collecting data for the meta-RL process. And let's say that the agent decided to look at the instructions and then just stay and watch the instructions. Does anyone have thoughts on whether that would be a useful trajectory or not for the learning process? Yeah, exactly. So it did something useful, but it doesn't get any reward for that. It only gets reward if it did that and then went here. And so that's also not going to be very useful for the learning problem. And basically you only, like, in the problem like this, you're only going to actually be getting good, like learning something useful about how to explore and exploit if you successfully did the proper exploration behavior and then did the exploitation behavior. And if you do them in separate episodes, then then you're not actually getting good learning signal. And that means that you sort of have this kind of sample complexity where you need to actually get lucky and do both of the two things at the same time in order to get signal that helps you learn the problem. So basically it's hard to learn how to explore and exploit at the same time. Another way to, another example of this is, say that you're trying to learn how to cook. You have data in previous kitchens. Your goal is to then be able to quickly learn how to cook in a new kitchen. Now, in order to learn how to cook, you need to find the ingredients. And if you haven't yet figured out how to find the ingredients because you had bad exploration, then you can't learn how to cook because you don't have the ingredients with you. And then you're going to get low reward. And then also, if you don't yet know how to cook because you haven't like collected experience on that, then regardless of the exploration you do, you're going to get low reward. And so you sort of have this chicken and egg problem between learning how to explore and learning how to solve the task using that information. And so there's another way to view this is this kind of coupling problem where exploration and execution or exploitation depend on each other in order to be jointly successful. So then the way to view end-to-end training is that it's great in that like you can learn this optimal trade-off, but it can be extremely challenging if you have a hard exploration problem because you need to figure out how to explore and exploit and get learning signal that way. The question is the ultimate challenge here that the reward is sparse. So it's true that if you had a dense reward, you'd be in a much better place because basically because you wouldn't really have to explore. You would be able to, you wouldn't have to explicitly take actions to explore. And this really comes down to a problem when exploration is hard. If exploration is easy, this really isn't a problem because you no longer have to solve both exploration and exploitation. You only have to solve exploitation. So there's a couple solutions to this, and we'll start to talk about one solution today. And then on Friday, we'll talk about more solutions. So the second solution, I'm not going to go into like complete detail on how these work, but one solution here is instead of optimizing just for end-to-end reward, you can add in auxiliary exploration objectives to encourage it to try to actually figure out something more meaningful about the task. And one approach here is to use what's called posterior sampling, also called Thompson sampling. And the way that this works is that we talked about having an algorithm where you're trying to infer what the task is. And if you've collected some experience so far and you've inferred some distribution over your task, in this case, Zi is now kind of some latent representation. It's not a representation that's known. Then what you could do is you could then sample from this distribution and then act as if that was kind of the correct task. So if you have like this task inference procedure, and then you also have a policy that, given an estimate of Z, is able to generate actions, then what you can do is you can sample a Z from this distribution and then sample from this policy. And if you have policies that are able to, this starts to kind of decouple the problem a little bit, because if you have policies that for a given Z are kind of do the task, then you would basically learn an exploration strategy that is trying to kind of go down the different corridors to find the solution. So as an example, this is actually a problem that looks somewhat similar to the corridors, where you get a sparse reward if you reach one of these circles, and the different circles correspond to different tasks. And in this case, we've sampled this task right here. And first we sample a Z from our kind of prior over tasks without we haven't collected any data yet. So we sample Z, we then run our policy based on those different Zs, and we get exploration based on these. And then we use that to infer what the task might be. And so now we know that the task is probably either over here or over here. And so now you'll collect trajectories that are lighter in color, that are like this one, and going over here. And then once you've actually collected this trajectory, then you should actually have a much narrower distribution over the task because you get positive reward here. And so then your policy, or your Z distribution will be narrowed out here, and you'll execute your policy according to those Zs. And so that's kind of one approach for addressing this exploration problem. Basically learning this latent representation over tasks, and then sampling from those tasks, from that distribution, and acting according to your policy for that task. Does anyone have thoughts on so there's some scenarios where this is great, and scenarios where this is not so great. Does anyone have thoughts on when this sort of sampling might be bad? Like what sort of MDPs this might not work well in? If you have a large action space, that could contribute, although it isn't just having to do with the action space, because if you have a dense reward in a large action space, you'd be probably okay. So if Z is out of distribution, certainly things will be problematic. But even in distribution, there's scenarios where this exploration strategy will be really bad. Yeah. So one scenario where this might work poorly is if you start to see some reward, but there might actually be even better reward in another scenario. You might kind of start to exploit a little bit too early, although it won't rule out those higher reward scenarios if it knows that there are other tasks that might have higher rewards. So I guess the scenario that I was thinking of, where I think that this can be quite bad, is actually a lot like this scenario right here. So the strategy that posterior sampling will learn in this scenario is, instead of looking at the instructions, it's instead going to go down each of the hallways and try to find the reward. Because it's trying to explicitly explore by executing policies corresponding to different tasks. And this will be especially bad if the hallways are very long. So if the hallways are really, really long, I don't know, take days to traverse, then what it's going to do is it's going to spend days going down one of them and then figuring out that it's not the right one, and then spend days going down another one, rather than trying to seek out information that might tell it about what to do. Cool. So, for example, if these goals are very far away and there's some sign that tells you what the correct goal is, then this is a bad strategy. Now, if that sign doesn't exist, then it actually would be a good strategy because you have to go down those different corridors. Okay. There's a couple of other approaches that we can use as well that include adding intrinsic rewards that try to encourage it to visit new states, and also trying to visit states that help you distinguish the dynamics and reward models for different tasks. So we try to collect data so that our model of rewards and states are accurate. And with this sort of approach, you could actually get exploration strategy that looks a lot more efficient, that looks something like this, compared to posterior sampling that's trying to kind of just sample the different trajectories for the different tasks. There's also scenarios where this might be bad if there's lots of distractors or really complex state dynamics. But fortunately, don't have too much time to go over that now. So these sorts of approaches are easier to optimize than end-to-end. A lot of them have some principle behind them, but they can be very suboptimal in certain environments, and it kind of depends on the environment or the domain.